Okay? So we now have our quotient group, right? Because what is a quotient group? Just a set of cosets. We have our 8 cosets, and we know it has to be 8 because we know the order of this and we know the order of that, right? 32, 4. And the size of a quotient group is the order of the group G, big G, divided by the order of your normal subgroup, H, right, which is 4. 32 divided by 4. Okay? So here are our 8 cosets. Right? Okay, so we have our group. The group is just a set of cosets. Now, to finish off, because we still have to decide this quotient group of order 8. Now remember, we did a whole chapter on the possible types, non-isomorphic types of groups. If I can find this quickly. Now, from chapter 15, so go back 2 lectures. We calculate, we actually analysed all possible types of non-isomorphic groups of order 8, and there were 5 of them. So I'll just mention them briefly here. There's the cyclic group of order 8, right? There was C2 times C2 times C2. That was the second possibility. There was C4 times C2. That's the third possibility. There was D4, the dihedral group of 4 sides. In other words, symmetry operations of a square. And there was Q4, the so-called quaternion group. Okay, so we know there are 5 different possibilities that this quotient group might be isomorphic to, because that's all there are. If your group is of order 8, then there are only 5 possibilities that this group could be isomorphic to. Okay? So which of those 5 is it going to be? Well, if you have a look at the cosets, now remember cosets are just elements in the quotient group, right? So as elements, they will have their order, right? The order of an element. So you can look at these 8 cosets, but thinking of them as elements of a group, right? These cosets are elements of a quotient group, of a factor group. Okay, so you're going to ask, well, what's their order? So if you go ahead and calculate the order of these elements, cosets, then you'll find, for example, this element of the quotient group, its order, if you actually calculate, go through the mechanics of it, you'll find its order is 8. But 8 is the order of your quotient group. Okay? So the order of an element is equal to the order of its group. Therefore, this group must be cyclic, right? If the order, go back quite a few lectures, if the order of an element is equal to the order of the group, that group must be cyclic, all right? And this coset, this element, if you like, of the quotient group, has order 8. Therefore, this is cyclic, and therefore this quotient group is isomorphic to C8, the cyclic group of order 8. Right? And that was one of the 5, right? Just briefly, C8, C2 by C2 by C2, or C4 by C2, or D4, or Q4. They're the only 5 possibilities you can have with a group that's of order 8, right? There are only 5 possibilities. So this one is of order, it's order 8, and it's isomorphic to C8, the cyclic group of order 8. Okay, so we now know what type it is. Alright, now I'll just briefly give you this last bit. Now it's just as detailed, it's just as much work as all this, but now you're familiar with these techniques. You know, take blocks of your cosets, you know, like 4 at a time or whatever, and eliminate the repeats. So the technique applied here will be much the same as here. Alright, so here's the quotient group. Again, Z8 by Z4. Oh, it's the other way around. Right, so Z4 by Z8. Okay, Z8 by Z4. Let me check that actually. I haven't mistyped them. Z8 by Z4, yes. Right. And here's your subgroup. Now, what is this? Remember these angular brackets? What is that? That's the it's the subgroup generated by an element. Now, this is an element. It's one of the elements of this, right? The elements of this, there'll be 32 of them. Now it's a direct product, right? So you'll have 32 ordered pairs, like A comma B, and A will range over 0 to 7, and B will range over 0 to 3. So you have 32 ordered pairs, right, in your set, well, group. Yeah, that's your big G. Right, so the order of your group G is 32. Now, what's the group generated by this element? Well, I've written it here. So the group generated by this, that's what the angular brackets means. You find the set or the group of increasing powers of this this member. So this to the power 0 is its hold on. This to power 1 is this, and do it twice. So you do this. In fact, in the context of residue classes, that's what these are. The binary operation is plus. Okay, so this squared, in effect, you know, this binary operation with itself, that'll give you, 2 plus 2 gives you 4, and you do it again a third time, so you get 6, and you do it again, you get 8, but it's mod 8, so that's 0. Okay, so your H here, your subset is this. Okay, 2 0, 4 0, 6 0, 8, and 0 0, or 8 0, or 0 0. Right, so that's your subgroup. Now it's plus. You're adding these. These are just integers, so it's a billion again. So this subgroup is a billion. This is a billion. Therefore, any subgroup is a billion. So therefore, this subgroup is normal. Okay, and once we know it's normal, then we know that a quotient group is possible. All right. What's the order of your subgroup H? Well, 4. You can just see it has 4 members. Okay, so the quotient group will be of size 32 divided by 4, so that's 8. So once again, we have 8 cosets, right? Quotient groups have, they're just a set of cosets, right? So we have 8 cosets again. Now go through all this analysis, and I'm just giving you the results now. So the cosets will be of the form 0 0 plus H, here's your H, and 0 1 plus H, 0 2 plus H, 0 3 plus H, and 1 0 plus H, 1 1 plus H, 1 2 plus H, 1 3 plus H. Right? So there are your 8 cosets, and the order of the quotient group is 32 divided by 4. Okay, so we'll have 8 cosets. There they are. All right. Now, just as here, well, here. here. Have a look at these members. Okay, they're cosets, but think of them as members of a quotient group. They're just members. Find their order, the order of the member, the member's order, the element, the order of an element. And you have these cosets that are elements of the quotient group. Find their order. Now, if you do that, you'll find that 4 of these 8 members of the quotient group have order 4. Okay. Now, of course, one of them will have order 1. That's the unit. Right? That's always true for any group. There's always one element that has order 1. That's the unit. Okay. So, and 3 of them will have order 2. Okay. So none of them have order 8. So we know that this quotient group here is not cyclic. Okay. So 4 of them have order 4 and 3 of them have order 2. So the quotient group is isomorphic to this form. Okay. So Z2 times Z4. Right? Okay, it's been rather a long session. I'll stop there, and the next session will be on problem solving.